So now I'm happy to present Tiarna Lee from King's College London, who's also actually in the FAME activity committee, so thank you for that. And Tiarna will be presenting on understanding AI bias in CMR segmentation. You have the floor.
Thank you. Okay, let me do the classic. Can you see my slides? Yes, okay, perfect.
Looks good.
So my name's Tiarna Lee. I'm from King's College London. I'm going to be talking about understanding AI bias in CMR segmentation. So firstly, what is CMR segmentation? Cardiac magnetic resonance is used for assessing cardiovascular diseases, and clinicians extract biomarkers such as ejection fraction for diagnostic decisions, as well as treatment planning. Using AI, some of these tasks can be automated, and we wanted to assess if the algorithms had any bias and where this bias comes from. So we use 352 end-diastolic and end-systolic short-axis cine images of the heart from the UK Biobank, which is a collection of medical data. It is approximately equally split in terms of gender, but it has, in terms of ethnicity, 80% white participants, and a variety of different smaller proportions of minority ethnicities. So to give you an overview, first we measured bias in CMR segmentation, namely sex and race bias. Then we looked at understanding the source of bias using race classification, explainability methods, and confounder analysis. So firstly, measuring bias in CMR segmentation, we used a segmentation model called NNUNet, and we varied the proportion of subjects with protected attributes in the training data with the hypothesis that an unbalanced training data set, for example, 100% of one group, would produce higher accuracy, better performance in this group in the majority, whereas a balanced training data set would produce equal performance for the two groups. So to look at the results in the figure on the right-hand side, on the x-axis, you can see the percentage of female subjects in the training data that was varied, and on the y-axis is the segmentation performance, which is measured using the DICE similarity coefficient. We found no statistical differences in DICE score looking at sex biases. But in terms of racial bias, we did find significant differences and found that Black subjects had a high performance at 50-50, where you would expect performance to be equal, but that the performance was not significantly different, i.e. fair, at 25% Black subjects and 75% white. To put this in context, we're in an area of London known as Lambeth, where the population is 55% white and 24% Black. And if you were to just consider white and Black subjects, it would be 70-30, which would look something like this in my experiments, and may not produce a fair model that would be applied to the population here. So then we want to move on to looking at bias in different segmentation models. So we firstly use UNet, which is a precursor to NNUNet, SwinUNet, which is a transformer-based model, and DeepLab v3+. We again vary the proportion of subjects in the training data set, but here we also controlled for the age of the subjects. So to show you these results, we once again found no significant differences by looking at NNUNet, but found significant differences looking at the other models. And we found that the models were only fair when the percentage of female subjects was over 75%. If you look at the race experiments, again, we found significant differences in UNet, but also SwinUNet as well. NNUNet and SwinUNet, but also found that for DeepLab and UNet, the models were only fair at 25% of the Black subjects in the training data set. So given this bias, we wanted to understand where it was coming from before we applied mitigation methods. So we looked to assess the distributional shift between Black and white subjects by training a race classification model. So here we use ResNet 18, and because the input is usually 3 channels and we have grayscale images, we chose to use 3 channels of either images, segmentations, or a combination of both. And we found that race could be classified with high accuracy using only images, producing an accuracy of 0.96. But race could also be classified using only segmentations, which produce an accuracy of 0.74. And so we concluded that the distributional shift comes mainly from images, but also partly from segmentations. So based on this, we want to localize the source of this bias and find where it's coming from. So we use GradCam, which is an interpretability method, to visualize the parts of images that we use for classification. This would produce heat maps like the one below to show which parts of images we used. So as an example, here's a picture of some flamingos from one of my holidays, the GradCam heat map in the center, and the image and the heat map on the right. So this is an example of the heat maps that we saw. So the GradCam method was used on the image dataset, and you can see that the model was using regions outside of the heart for classification, but also some artifacts that we found as well. So we had a hypothesis that differences in MRI scan year were causing these differences in artifacts. So we repeated the segmentation experiment, but controlled the subjects for MRI scan year. And we found very similar results between the original experiment and controlling for MRI year. So we concluded that the artifacts were a spurious correlation with race, but not actually the source of the bias. So based on the GradCam experiment, we wanted to further investigate which regions we use for classification. So we trained a classification model using images with the rest of the body, like apart from the heart, cropped out, which you can see on the left, and images where the heart was blurred out, which you can see on the right, to find out where the distributional shift comes from. So we found accuracy decreases to around chance if you crop the images around the heart, but that the accuracy was much higher. In fact, it was similar to the original images when using images where the heart is blurred out. So based on these experiments and the fact that the accuracy decreased to chance when using images cropped around the heart, we used these same cropped images in segmentation, repeated the segmentation experiments, and found that the bias trend is less, but that the bias still exists. It's important to note here that we don't propose using cropped images as a bias mitigation method, because in clinical practice, you would need the ground truth segmentations, which aren't always available. But instead, this was a test of the bias. So since this bias still existed, we wanted to look at the latent representations of the images. So if you take, for example, this unit, we took the representations at the bottleneck of the encoder part of the network of NN unit and formed PCA on these representations. So as you can see on the right, you can see that the representations, the PCA of the representations are linearly separable. But we want to test this formally. So we use a logistic regression model to see if you could classify race from the PCA of these representations, and found that you could classify race with 0.95 accuracy, which is very high. So, could confounders explain the differences in segmentation performance? In short, the answer was no. We used a linear regression model to investigate the correlation between dice-score and confounders, and found that for the white subjects, no confounders could explain the differences in performance. But for the black subjects, a left ventricular stroke volume, ejection fraction, HDL cholesterol, and MRI year, which we tested, were correlated with dice-score. So to conclude, biases can be seen between different races, but sex bias was only seen in some segmentation models, for example, UNET. The scale of the bias differs depending on the segmentation model, and non-heart regions, such as subcutaneous fat, so fat underneath the skin, appear to be a significant source of bias, but not the only one. In a clinical context, less bias means more accurate models and better performance for everyone the model is applied to. This means more accurate estimation of clinical biomarkers and better treatment outcomes and planning. So in future and current work, we're still trying to fully understand the source of the bias and how it can be mitigated. We're looking at other possible confounders and controlling for them. And overall, representative data sets are the ideal solution to this problem. But barring this, you should try to aim for reasonable representation of subjects and thoroughly assess models for bias. Thank you.
Thank you very much. So again, the Q&A is open to participants. Please type your questions and I'll relay them to the speaker. Again, to start off, while the questions are coming in, I was wondering, so you investigate the influence of different variables, but do you think there are differences in the combinations of variables? So if you sample, like different proportions by sex, it might also change the proportion by age, for example, or do you take that into account somehow?
Yes, so we took this into account by controlling for example, in the first segmentation experiments, by controlling for age. So each subject had, if you're looking at males and females, there was for each female a partner male subject whose age was plus or minus 1 year of their own.
Okay. Oh, that's great. So a question from Caroline Petitjean. Do you have any report publication about your work available online? So I guess this was either at the workshop or MICAI this year, right?
Yes, there are two publications if I go back. One of them is here, a systematic study of race and sex bias in CNN-based cardiac MR segmentation. That's one of them. And the other one is at the bottom here, an investigation into the impact of deep learning model choice on sex and race bias in CMR segmentation.
Great. So yeah, we will have, I think, the recordings of the talks online so you can find all the info.
And I think they're also on the FAME website as well, under resources.
Great. We have another question from Carlos Garcia Cabrera. Do typical augmentation methods mitigate these biases or the opposite? And secondly, do MRI-specific augmentation mitigate the biases or the opposite? Thank you. Very interesting presentation.
That's a very good question. So one of the methods that has been proposed is using different augmentations for different protected groups. So for example, if one group is performing better or worse than the other, changing the augmentation to like improve performance for that group. The second part about MR related augmentation, I don't know if you mean during like MR reconstruction, possibly. I don't know if that's related to bias.
Okay, so you will also be able to comment on because there are more questions coming in that we won't all have time for, but they will remain in the Q&A if you want to follow up. So maybe a last question, given the time. Have you seen from Mustafa Ghazi, have you seen if the differences in model performances may come from data augmentations built into some models like the NNUNet?
So all of these, well, it's good that I've got this up because all of these four models use the same augmentation, but we did do a sort of preliminary experiment on NNUNet and found that the data augmentation didn't have an effect on the bias that we saw. So that's specifically to NNUNet, but the differences in augmentation there didn't have an effect.
Yes, thanks a lot. So let's thank the speaker again.